All right. Thank you, and thanks to the organizers for the invitation. I'm really happy to be here. And my goal today is to convince you to think of shape as really an organizing principle for data analysis. So what does that mean? I mean, in simple terms, it means that data has shape and that that shape has meaning. And more than that, that the shape, in fact, carries the meaning of the data. So whether or not you think about your data analysis in this way today explicitly, I claim that you already know this, and in fact, you use this fact every time you do any kind of data analysis. So what does that mean? Well, suppose you're fitting a linear regression, right? You're assuming that your data has a particular shape, that it is sampled from somewhere near a line or near a hyperplane in space. And if your data does have that shape, you can fit a line or a hyperplane to it, and that will be a very effective model. It'll allow you to do prediction. It will allow you to describe your data in a simple way, and that's great. Of course, if your data doesn't have that shape, that model will perform really poorly. Different examples, say you're running a clustering algorithm. Again, you're making an assumption about your data's shape. You're assuming that it's split into different clusters, that those clusters are relatively well separated, and that themselves, they're kind of nice and coherent little buckets. If your data has that shape, your clustering model will fit well, it will give you a nice result, and it's a good description of your data. If it doesn't, if those clusters kind of meld into each other, or they have very different densities, or the clusters themselves are not like nice, well-formed clusters, that model won't work so well. Okay, but your data could have other shapes, right? It could be a circle. You have some kind of recurrent periodic behavior. You might see this kind of shape in your data. There are methods for dealing with or fitting models on these kinds of shapes. They're more obscure, but they're out there. Maybe your data looks like this. Maybe it looks like some kind of central core, and it has different peripheral components describing different ways that the data can be not in the central core. Okay? Now you have no out-of-the-box method for fitting a model like this, but it's a perfectly reasonable shape that your data could have, and you'd really like to just say that that's its shape. So in all of these cases, right, the shape drives your choice of model, and it drives the effectiveness of the model that you fit. So shape is really the fundamental principle here that you're using to do your data analysis. And what you'd really like is a method for just understanding that shape from the beginning. So mathematics offers you two ways of understanding shape, geometry and topology. And the two ways of understanding shape differ in the rigidity with which they regard or define shape. So geometry is the familiar one. And in geometry, the key notion is a metric, a notion of distance. In geometry, two shapes are the same if you can get from one to the other with an isometry, a map that preserves the distances between any pair of points. So that means that you can rotate shapes, and they don't change. You can move shapes around, and they don't change. You can reflect them, and that's about it, right? Those are the ways that you go from one shape to another without changing any of the pairwise distances between points. Topology has a looser notion of what shape means. It says, I don't care about distances per se. What I care about is locality. So I can map one shape to another while preserving the local neighborhood of every point. Then I'm going to say those are pretty much the same shape. So what that means is that I can now stretch. I can stretch the circle into an ellipse, and points that started out nearby each other, they're still nearby each other at the end. So that circle and ellipse, those are the same topologically. I can round off corners, so I can turn the square into a circle, and I say those are essentially the same shape, because points that used to be nearby each other are still nearby each other. I've preserved this notion of locality. So those are the two notions of shape that come out of mathematics. Which of those makes more sense for data analysis? Well, how much do you believe the scale in your data? The scale of any individual feature, the scale across different features, the relative scales. Personally, I don't really at all, because my data comes from healthcare or finance or real-world situations where those scales probably don't mean anything at all. And if they do, I probably don't know about it. So for those kinds of situations, topology is a much more natural choice than geometry. So I'm going to describe to you a method for capturing shape in the topological sense. We're going to do this first on some toy data sets, and then I'll show you some real examples. So here's a toy data set. This data is sampled noisily from near a circle, right? And don't worry about the colors right now. They're just to help illustrate in a few minutes, right? It's a two-dimensional data set. It is a circle, and we would like to just capture the fact that it is a circle. So we're going to do that with a function that we call a lens. This is any real valued function. And in this case, that function is going to be projection onto the y-axis. So projection onto the y-coordinate for each point. In the range of that function, we define a number of bins, and the bins overlap, right? They fit together like this. Now I'm going to look at which data belongs in each bin, right? The inverse image of each bin, which data got mapped into it. Now, because there's overlap, some data is in more than one bin, right? So if we go back, right, the orange points, they double up. They were in more than one bin. Okay. Within each of those bins, we're going to run a clustering algorithm. Doesn't particularly matter which one. It's robust to that kind of a choice. And record the output of that clustering algorithm with nodes in a graph that we're going to produce. So in the top bucket, right, that arc clustering algorithm probably says that's one cluster, so we record that with one node over on the right. In the second from the top bucket, there are two clusters there, one on the left, one on the right. We record that with two nodes. Third bucket is also two clusters, and the bottom one is a single cluster again. Now, because there was overlap between the bins, some data points ended up in more than one cluster over on the right. When that happens, we record that by connecting the two corresponding nodes with an edge. So the orange points on the upper left and the orange points on the left middle bin were the same. They ended up in the top cluster and the top left cluster. We connect those with an edge. And we do that around the whole circle, and we get this graph. And this graph exactly captures our original shape. It's a circle. Hooray! So that's the fundamental idea. So this is a toy example, but I'm going to show you some more. What does this tell us about this algorithm? Well, basically what this algorithm is local clustering, right? It's local clustering, but there's two smart pieces here. The first one is that we're keeping track of how the local clusters are related to each other. So the edges here are just as important as the nodes. They're telling us how those local clusters are related to each other. And the second smart thing here is that the notion of locality is defined by the values of a function. So I used projection onto the y-coordinate, but we can use any real valued function. And if we use a more interesting real valued function, we'll get a more interesting result. So this turns out to be a very powerful and flexible algorithm because of the different ways that you can choose that real valued function. And of course, you can use more than one function, and there's lots of ways to extend this. So here's what that looks like when you use a more interesting function. So what you see on the left is a simple, again, two-dimensional data set, and it's colored by a density estimator. So very dense, points with very dense neighborhoods, lots of other points around them are red, and points in more sparse neighborhoods are blue. So what happens when we use density as the real valued function in this algorithm I just described? Well, first, it means that we do our local clustering in bins defined by density, right? So first, we cluster the very dense stuff. The very dense stuff is the dark red. How many dark red clusters are there? Just one. Then we cluster the somewhat less dense stuff, the red but not dark red. There's two clusters of that. Right? There's some regular red stuff up near the dark red stuff, and there's some down in that right-hand side cluster. So we record that as two clusters, and there's an edge there because the dark red cluster and the normal red cluster had some overlap. Okay. So now we cluster the orange stuff. There's some orange stuff near the top cluster and some near the right-hand side cluster. And similarly for the yellow. There's some yellow near the top cluster, some near the right-hand side cluster. So we see these two, we record these two clusters and the connections representing the overlap with the clusters we looked at before. Okay, now what happens when we get to the blue? Oh, sorry, green. It's hard to see the green. So there's some green up near the top cluster. There's some green towards the outer edge of the middle cluster. And there's some green right in the middle of the big blue kind of exploding cluster, right? So those are our three pieces. Some are connected to the clusters we've already been looking at, and one is new. When we get to the blue, there's no longer really any blue in the right-hand side cluster, but there is blue in the bottom and in the top, and they're separated. When we get to the darker blue, there's really only one cluster of this royal blue stuff, right? That's when the top and the bottom clusters have kind of melded into each other. And when we look at the really dark blue stuff, it's kind of sparse out on the edges, so there might end up being lots of clusters of that. Okay, so this is the graph that we produced. So how do we interpret this graph? Well, we see that the large-scale structure of this graph is first, there are two connected components, right? There's the middle piece with 4 nodes and 3 edges, right? That's corresponding to that cluster that's separated off by itself. It's its own connected component of the graph, and it's a cluster that's well separated from the rest of the data. And then there are 2 other clusters, and we see that because there are 2 branches on the other connected component of the graph. One of them is a cluster that has some really high density stuff, and one is a cluster that has only lower density stuff, and they meld together. Right, so this network gives us a map of that original data set. When we apply this method on real data, not toy data, we see much more complicated networks, much bigger networks, but the interpretation is the same. So the nodes in these networks came out of the clustering part of the algorithm. So nodes represent groups of similar data points. The edges came out of connecting clusters that had overlap, and so the edges connect similar clusters. And what we're interested here is the graph, not its, as a combinatorial object, not its position on the screen. And so we can stretch and move these graphs around, and it doesn't matter. So when we look at a large-scale graph like this, what we're looking at is the major features of the graph. That's how we're interpreting it. So I look at a graph like this, and it's not so much the individual nodes and edges that matter as saying, well, it looks like there are 1, 2, 3 major clusters in this data, and one of those clusters splits into 2 smaller clusters that are somewhat connected but pretty loosely. And then up in the right-hand top corner, there's a bunch of outliers, points that don't really connect to anything else in the data. And so that's how you read an output like this. I think I'm going to skip that example because I want to give you a couple of real-world examples instead. So here's a real-life example of how a topological approach can really change your understanding of a phenomenon that you're studying. This example comes from a collaborator of Ayasdi's, David Schneider at Stanford, and he studies disease progression. So the traditional mental model of disease progression is pretty simple. It says you can be healthy and you can be sick, and there's a continuum of states in between healthy and sick. And that's fine, that makes sense, but it turns out that when you look at the data on this from a topological perspective using the algorithms I just described, that's not what you see at all. What you see is that there is healthy and there is sick, and you can go from healthy to sick, and you can go from sick to healthy, but those 2 paths are not the same. That the way your disease progresses as you're getting sick and as you're getting better are distinct. And so the right mental model for disease progression is not a continuum, it's a loop. And this is such a fundamental result that it shows up across different types of data sets and across different organisms. So it shows up in people, and it shows up in mice, and it shows up in bacteria, and it shows up whether you're measuring gene transcriptome, whether you're measuring cytokines, whether you're measuring clinical data, and across several different diseases as well. It's a fundamental fact about our understanding of disease progression that's really encoded in the shape of that data. So the second example, which comes from one of our healthcare projects, is looking at Carepaths. So Ayasdi has studied perioperative care paths, which means the sequence of events that happens to you right before and right after you have a surgery. So in this example, we're looking at total knee replacements. We have data from a healthcare provider system that's done a lot of total knee replacements. So the way that we think about this data is we say that each sequence of events in a total knee replacement is a single data point. And we come up with a way of measuring the distances between those sequences of events so that I can say, the sequence of events characterizing your total knee replacement and this other person's, they're this far apart. But characterizing your total knee replacement and somebody else's total knee replacement might be, further apart. Anyway, it's the event sequences themselves that are the data points, and then we have a way of measuring distances between them, and that gives us a metric space of Carepaths. And then we study that metric space topologically using the algorithm that I described before, and we get a map like this. Right? So this shows you different regions of that Carepath space. It shows you regions where similar Carepaths have been grouped together. So up in that, so we call that long kind of piece sticking out a flare, right? So up in that flare that's circled, there's a group of paths where we see that the length of stay for those patients is all relatively low. There's also a little pocket down over on the right-hand side flare where we also see that there's a group of patients that have really low length of stay. And we could look at other measures, other outcome measures as well, quality outcomes or cost outcomes or whatever, right? And we could look for groups of Carepaths where people do well on that quality measure. Then we say, well, what is it about that particular group of Carepaths that's causing good outcomes? Or at least can we describe, we know that those are all similar Carepaths where that low length of stay is happening. Can we describe what's a representative or consensus Carepath out of that group? So we do that, and that's the basis for this tool that we built as a decision support tool for physicians that allows them to build and modify Carepaths and to say what different Carepaths look like for different groups of people. So they can take that group of people who had unusually low lengths of stay for their total knee replacements, they can look at what is the Carepath that's common in that group, and they could emulate that with other patients. So it's a novel way of looking at this event sequence data and this problem, and it turns out to give this really nice tool for physicians. So to close out, I want to go back to the world of the theoretical and talk about one more advantage of sort of thinking topologically. So there's an asterisk here because I'm a mathematician and I can't quite bring myself to say beating the curse of dimensionality without an asterisk. But it is giving you a different way to think about the curse of dimensionality. So the curse of dimensionality is this phenomenon that people know about, right? That when you analyze very high dimensional data, the sample size that you need to capture a given, say, fraction of the volume in your space, it grows exponentially as your dimension grows. So that as you study higher and higher dimensional problems, you feel like you need such a massive amount of data that you could never hope to have enough. So topology gives us a different way of thinking about this, because in topology we differentiate between the intrinsic dimensionality of a shape and the dimension of the space that it's embedded in. So picture a plane that's been sort of twisted and maybe it sort of looks like a saddle, say. Right? That plane is a two-dimensional object. If you were writing down a parametric equation for it, you would need two parameters. It might be embedded in 3 dimensions so that you can see that saddle shape. You could embed it in 100 dimensions or 1,000 dimensions, but the plane itself is intrinsically still 2 dimensions. And what this result says, this is a really nice result from a couple of famous topologists, Niyogi, Smale, and Weinberger, and what this result says is that to detect the key topological features of a shape, the sample size that you need depends on the intrinsic dimension of the shape you're studying, not on the dimension of the space in which it's embedded. So if you're looking at that plane and your data is distributed, supported near that plane, then you can detect its key topological features. You can know that it's a plane from a sample whose size depends only on the dimension of the plane, to whether that plane is embedded in 100 dimensions or 1,000 dimensions or 1,000,000 dimensions. All the rest of those embedding dimensions are irrelevant because the actual pattern, the actual shape in the data is just those 2 dimensions of that manifold. So this is, again, sort of an argument that topology is a really useful and natural way for looking at the analysis of complex and high-dimensional data. So with that, I'll close out, and there's a lot more to say about topological data analysis, but I know I don't have a lot of time, so you're also welcome to find me. I'll be around all afternoon and happy to talk to anybody who wants to.
Yeah, let's thank Allison.